Friends, in last few sessions we looked at what I will call our second module, namely relating to the complex reactions, and in today's session we will look at few examples, we will solve few examples with problems related to complex reactions, their kinetics and so on. But before we do that, let us recap what we have seen in this particular module. So, we started by looking at analysis of simple complex systems. Now, you may wonder what is simple complex system. Simple complex system are the ones where we said that there are few reactions, but they are enough to capture the complexity of the system. So, we looked at, for example, series reactions, parallel reactions, series parallel reactions and few other cases. Now, the moment you have more than one reaction, your conversion alone cannot be your design criteria, because if reactant, for example, is undergoing parallel reactions. So, A1 going to A2 as well as A1 going to A3, then conversion of A1 alone is not sufficient to tell us what is happening with respect to A2 and A3. And as it usually happens, one of these products and therefore, the reaction is an important or desirable reaction, whereas the other reactions are not desirable reactions. So, under such situations we need to go beyond conversion and start looking at what is the yield of the product, for example, or what is the selectivity. So, in the example we mentioned, suppose we have a parallel reaction set, A1 going to A2 and A1 going to A3. Then we talk about what is the yield of A2 on the total A1 consumed, or what is the selectivity of A2 over A3, and we start working with those yield and selectivities, and these in turn often determine how we can choose our reactor, that is, if you want to maximize yields, maximize selectivity and so on. We then talked about two important concepts which are required for arriving at the kinetic rate expressions for such complex network of reactions. Those two concepts were namely quasi steady state and quasi equilibrium approximations. What is a quasi steady state approximation? We said that there are few intermediates or few species in our scheme of things whose turnover is very large. That means, they get formed, they get converted to other forms, and this is fairly a fast process. So much so that as soon as the reaction starts, there is quote unquote steady state achieved with respect to few of the species, not all the species, because if there is a steady state with respect to all the species, there is no net conversion. So, rate of reaction would be 0. So, it is with respect to few of the reactive species that we invoke a steady state approximation. So, its concentration does not change, and therefore, we say that we have a quasi steady state approximation. On the other hand, we also can think about reactions and their rates rather than focusing on the species, and say that few of the reactions are very fast compared to other reactions. So, the slow reaction is therefore what determines the rate of the reaction, and in the time scales of these slow reactions, the fast reactions has already achieved equilibrium, and therefore, we say that those reactions are at equilibrium. Again, not the entire reaction set or reactions are at all reactions are at equilibrium, because if that is the case, then the rate of reaction would be 0. So, we have again what we call quasi equilibrium approximation. Now, using these two ideas of quasi steady state and quasi equilibrium approximation, we looked at kinetics of few of the reactions or few types of reactions, namely chain reactions, catalysis, some polymerization reactions and so on. We also then looked at certain class of complex reactions where you have large reactions, large number of reactants, large number of products as well as reactions. But what is further complicating the situation is that there is no way of defining the chemical species involved in this reaction, just as we can do ethane, methane, propane and so on. Take for example, crude oil. Now, who knows what all things are there in the crude oil, but we have fairly good idea that it contains aromatics, it contains aliphatics, it contains branch aliphatics and so on. So, can we for example, consider this quote unquote unknown species as consisting of few groups of species rather than individual species. And if that is the case, so what essentially we are doing is whatever aromatics that are there, for example, benzene, phenol, xylene and so on, we will call all these species as aromatics. We will lump all these species into a single species, which is not a real species, but an hypothetical species called aromatics, and then have few such groups and see whether the reactions can be represented with the help of these few groups of species. This is what is called as lumping analysis, and there we saw that what is required for lumping to be possible. So, what is the lumpability condition and so on. So, with this summary of things that we have seen, let us try to address or let us try to solve few problems that one may encounter or few types of problems in this session. The first problem refers to that in the synthesis of phosgene COCl2 from carbon monoxide and chlorine gas consists of several reactions, but in order to determine the kinetics of these reactions, two mechanisms have been suggested. Mechanism A, in which we have chlorine gas breaking down to chlorine atom interacting with carbon monoxide giving COCl radical, and this combining with another molecule of Cl2 giving rise to COCl2. Okay. So, this is mechanism A, and mechanism B is also starts with the same breakdown of chlorine atom, and but this chlorine radical interacts with Cl2 and then gives trichloride Cl3, and this Cl3 in turn interacts with carbon monoxide to give us phosgene gas. So, we have these two sequences with us. The question is, can correct sequence be determined by the experiments, kinetic experiments, whatever those experiments are required. So, we have to, if you recall, we talked about what are the various steps in determining the kinetics, and one of the last step or one of the essential steps is that once you have proposed the mechanism, it has to be verified experimentally. How do we do that? So, we have a mechanism, we make certain assumptions, we get the rate of the reaction, and then carry out experiments and see whether our experiments match with our mechanism or the rate expression that we have got with mechanism and certain assumptions. If it matches, that is not a guarantee that that is the correct mechanism, but if it does not match, that is a sure guarantee that our mechanism or the assumptions involved are incorrect. So, this example what we are trying to figure out is that there are two different possible mechanisms, and I have set of experiments. I can do experiments with carbon monoxide and chlorine at different concentrations, let us say measure their rate and so on. So, can I differentiate between these two mechanisms by looking at the reactor the experimental data. So, the first step that we need to do therefore, is that for each of the mechanism we must determine the rate expression, and we will start our problem solution with this analysis. Here again I would like to point out that our question was only to just see whether we can differentiate. So, on paper it looks like that is the only question, but we have to make a judgment what is the real question. So, it turns out now in this particular case the real question is to derive the rate of the reaction based on the sequences given, that is part 1, and then part 2 to see whether both these rate expressions are similar or is there any difference, so that we can design experiments to see what data we actually get and whether it matches with our sequences. So, let us start by deriving the rate expressions for the respective mechanism. So, our first mechanism is as follows: Cl2 gives rise to 2Cl. Okay. Let us call forward rate constant of this as k plus 1 and the reverse one as k minus 1. So, that is step 1. Then the second step is Cl plus CO, COCl. Let us call the forward rate constant plus 2, the reverse rate constant minus 2, and then COCl plus Cl2 COCl2 plus Cl. So, now let us try to derive the rate expression, and we will try to do it by starting with quasi steady state approximation. So, what we will do is we will try to go it in a systematic manner, that having said these are three reactions. So, we have reaction 1, reaction 2, reaction 3. We have 3 reactions. So, first let us define the rates of these reactions, and the reason why we should do that will become clear as we go along. So, let us say the rate of first reaction, and remember we are talking of intrinsic rate, is k plus 1 concentration of Cl2 minus k minus 1 concentration of Cl and whole square, assuming it is a what is this? This is follows law of mass action kinetics. So, they are elementary reactions, they follow law of mass action kinetics. Let us write similarly for R2, which will be k plus 2 concentration of chlorine concentration of carbon monoxide minus K minus 2 concentration of COCl. So, this is my second reaction, and for third reaction we will have K 3 into concentration of COCl into concentration of Cl 2. So, these are my 3 rates for 3 reactions. Okay. Now, let us, so first step, these are my rates, okay, rate expression. Now, we will write our mass balances for 3 species. Now, if you look at the reactions, we have chlorine, which is our reactant, carbon monoxide, which is our product reactant also, and phosgene COCl2, which is our product. What are the other species in the reactions? It is chlorine radical and COCl radical. So, radicals being an active intermediates, we can invoke the quasi steady state approximation for these 2 radicals. Okay. So, I will write mass balance for d dt of CCl. This is assuming okay, this is assuming that I have this particular reaction. So, what is happening? Cl must be 2 into R1 getting formed in the first reaction, getting consumed in the second reaction minus R2 and again getting formed in the third reaction, right. Okay. Let us write the mass balance for COCl. What is happening to COCl? It is getting formed in the first reaction and getting consumed in the second reaction. Okay. So, R2 minus R3. Okay. So, this is how our rate expressions will look like, and remember we have this 2 particular reaction sets, that is R1, R2, R3 and so on. So, let us invoke quasi steady state approximation. So, set it to 0 and solve it, we will get the following. So, all we are going to do is this R2 okay, all we are going to do is take this R2, R3, R1, use the quasi steady state condition and solve this, and this is what we will land up with and from this my rate of phosgene production, which is K 3 into concentration of COCl, we will get as COCl into concentration of Cl 2. So, we will get it as K 3 into all these terms that we had before for concentration of. So, I am just substituting minus 2, and so this is my rate for mechanism A. Now, if I go through the same series of steps for mechanism 2 B, which is given here, Cl 2 going to 2 Cl, Cl plus Cl 2 going to Cl 3 and Cl 3 plus CO going to COCl 2 plus Cl, we will end up with, I will not repeat the same calculation, but same writing the rates, and we will get the following. This should read plus 2. Okay. So, this is my rate for mechanism 2. So, now this is what we have got as mechanism 2. Now, our question is, can our experiments distinguish between these two mechanisms? Now, if you examine these two rate expressions A for mechanism A and B, one thing we notice that the numerator is same. Okay. It is some kinetic rate constant, all these things, kinetic rate constant, concentration of CO into concentration of chlorine raised to 3 by 2, it is same in both the cases. So, if in our real reaction, if denominator was some constant, then these two mechanisms are indistinguishable. Let us examine the denominator of these two rate expression. The first one, mechanism A. In the first mechanism, the denominator has a term containing concentration of chlorine, and in the second mechanism we have denominator which contains concentration of carbon monoxide, and the second term is again a constant. So, in this denominator terms, if for example, this term was very small, that is if K3 CCO was very small compared to K minus 2, or for mechanism A, if K3 CCl2 was very much smaller than K minus 2, then what will happen? This term will be 0, this term will be 0, in which case both these reaction rate constants are, both mechanisms A and B are simply some rate constant K prime, let us say concentration of carbon monoxide, concentration of chlorine raised to 3 by 2, indistinguishable. What was the condition required for that? That K3 CCO should be very small. Now, what does that mean in terms of mechanism? If we go back over here, if we go back over here, what does it mean? What is K3? First of all, K3 is this rate constant. If K3 is very small, then what will happen? What are we actually doing? We are assuming that the third reaction is very slow. That means, we can go back and invoke quasi equilibrium approximation, where we say that reactions 1 and 2 are at equilibrium. So, R1 is equal to 0, R2 is equal to 0, this is my quasi equilibrium, and the rate equal to K3. So, if indeed according to whatever mechanism the reaction is taking place, there is a rate determining step which is of the form of like a third reaction, and the first two reactions are very fast, then there is no way we can distinguish between these two mechanisms. Okay. But let us say that that is not the case. That is not the case. So, these terms cannot be neglected. So, they are there. So, let us go back and I will write these rate expressions once again. Mechanism 1, K prime CCO CCl2 raised to 3 by 2, some constant K double prime Cl2 plus K minus 2, and mechanism B, some constant. So, let us say that this third reaction is not really as slow compared to other two reactions. So, quasi steady state is reasonable. Then is there any way of differentiating between these two species? Now, given that the rate expression, these two rate expressions, given that the rate expression is obtained in these two different forms, let us see whether we can do some experiments, and let us say we do experiment with high concentration of Cl2. Okay. Now, if we do with very high concentration of Cl2, then what happens if for the mechanism A? For mechanism A, if this particular term is, what does it imply? It implies that K okay, very high concentration. I mean, that is all, high, low are all relative. So, this is what we mean when we say high concentration. Then what will happen to this mechanism? This term will go to 0, this second term, and we will get R as K prime divided by K double prime CCO CCl2 raised to half, because numerator denominator will cancel. So, at high concentration of Cl2, order of reaction with respect to Cl2 is half. At low concentrations of Cl2, again when this term is negligibly small with respect to K minus 2, what is the order? So, this is at high. So, at low CCl2, order with respect to Cl2 is 3 by 2. So, indeed if we do the experiments with high and low concentration, plot ln CCl2 versus ln R, and we have seen that the slope of this line is what we call order with respect to chlorine. Then if my data points are such that at low concentrations the slope is 3 by 2, but at high concentrations the slope becomes only half, then my mechanism A is correct. What about with respect to carbon monoxide? With carbon monoxide, with high concentrations or low concentrations or whatever concentration, the order is always 1. So, this is, so what is the summary? Mechanism A is correct if high Cl2, low Cl2 and carbon monoxide, the orders are half, 3 by 2 and 1, then mechanism A is correct. On the other hand, what if mechanism B is correct? What if mechanism B is correct? So, what I will do is I will put I will slightly modify this so that we get everything. So, let us say that we do experiments and look at the order n, high Cl2, low Cl2, high CO, low CO. Okay. And if the orders are half, 3 by 2, 1, 1, then mechanism A is correct. But if we use the same logic with respect to chlorine, if the order is always 3 by 2, and with respect to high concentration of carbon monoxide, order is 0 now, because both these terms will cancel, this term is negligibly small, and if with respect to low carbon monoxide the order is 1. So, what are we looking at? If our experimental data follows this pattern as shown by the violet color this thing, then we will say that our second reaction mechanism is correct. So, this is how we can distinguish by designing appropriate experiments to differentiate between the two kinds of mechanisms. Okay. So, this is our first problem. Let us look at another problem. Okay. And this example is from biology or biochemistry to be more specific, but again it has to do with chemical kinetics. What does it say? It says that liquid phase reaction S going to P is catalyzed by an enzyme E present. So, catalyzed by an enzyme E, that means enzyme E is a catalyst. Substrate S binds rapidly and reversibly with E to form a complex. The complex breaks down irreversibly and at a slow rate to give rise to product P. An inhibitor I present in the liquid binds rapidly and reversibly with the enzyme substrate complex and makes complex inactive. Okay. So, this is a description of observed of our mechanism. So, what is our problem now? Our problem is write down the sequence of elementary reactions describing the above process, derive the rate expression for consumption of substrate and compare it when inhibition is absent. So, what it means is what is written in English has to be translated in form of network of reactions, which represent the mechanism of this reaction S going to P. So, let us see how we can do this. The second part is deriving the rate expression, for which we will use the same methodology that we have used in our first example. So, what is this liquid phase reaction S going to P in presence of the catalyst or enzyme E? Okay. So, let us come to the second statement. Substrate S binds rapidly and reversibly with E to form complex. So, let us put that information in the form of a reaction. So, our reaction is S going to P in presence of this enzyme E, and what is happening? The first statement said S binds with E rapidly and reversibly. How do we put rapidly? We can't put rapidly, but we can put information reversibly. That means, this is a reversible reaction giving rise to a complex ES. Then, so we have taken care of the first part of the statement. Not completely, because we do not know what to do with rapidly, but let us do. So, what is the next information? The complex breaks down irreversibly and at a slow rate to give product P. So, this complex which has been formed breaks down irreversibly to give rise to product P, and enzyme must be regenerated, and it is a slow reaction. Now, whether the information that is its rapid, slow, we will use it while deriving the rate expression. So, this is my step 2. So, we have taken care of our second piece of information. There is more. An inhibitor I present in the liquid binds rapidly and reversibly with enzyme substrate complex and makes the complex inactive. So, we have to incorporate this third piece of information into our description of reaction. So, what happens? Some species inhibitor I called inhibitor binds rapidly with substrate enzyme complex, rapidly, reversibly to give, let us say, a complex ESI, and makes this complex inactive. That means, no product can be expected from this complex. So, this are the three pieces of information that is available to us. So, we have, let us say, our reaction 1, reaction 2 and reaction 3, and we want to find the rate of this reaction. So, the problem is what is the rate of substrate consumption or rate of product formation, which should be one and the same, because the reaction is simple, S going to P. So, let us see how we go about doing this. Now, what did our problem statement say and which we have not used so far? It says that, for example, the first reaction is rapid, the third reaction is rapid. What does it mean? That means and the second reaction is slow. It means that we can use quasi equilibrium approximation for deriving the rate expression, because rapid, two reactions rapid and the third one is slow, is an indirect way of saying that the second reaction is the slow reaction, is the rate determining step. So, we can invoke that quasi steady state approximation. So, once again if I write k plus 1, k minus 1 and k plus 3, k minus 3 and k 2 as my reaction rates, then I can write quasi equilibrium for reaction 1. So, what is my R1 now? R1, which is k plus 1 into concentration of S into concentration of enzyme minus k minus 1 into concentration of enzyme and substrate, is this is equal to 0. Okay. Same thing for R3. So, what will this tell us? This will tell us that if I write k plus 1 by k minus 1 equal to some rate constant k 1 capital I, then this will tell us that k 1 into C s into C e is equal to C E s, right. I can do the same thing for third reaction, because that also is a rapid reaction. So, for my third reaction, if I do the same thing and denote the rate constant k 3 as k plus 3 by k minus 3, then k 3 into C I into C E s is equal to C E s I. Okay. So, I have two pieces of information. And the third information, namely, we had used this earlier also, that whatever may be the active site, total active sites on my enzyme, as per this mechanism, some of these active sites have nothing bound to it, some of it has substrate bound to it, and some of it has enzyme, substrate and inhibitor bound to it, and there is no other possibility. Why? Because that is what we had in our mechanism. So, now if I use information 1, information 2 and information 3 and do little bit of algebraic manipulation, I will get my rate as constant k 2 into k 1 into C s into let me first write C t into C s divided by 1 plus S into k 1 into 1 plus k 3 into I. This is my final rate expression. Now, you can see what is the effect of I. For example, if I was not there, inhibitor was not there, then what would this rate expression boil down to, that is I is equal to 0, then this one would be K 2 K I C T into C S divided by 1 plus, sorry, this should read C S and C I, K I into C S would be my rate expression. So, what has happened because of inhibitor? Because inhibitor, this is the expression if C I is 0. So, what has happened because of inhibitor? Because of inhibitor, our rate expression has become independent of, or because of inhibitor, the rate is now lower compared to if inhibitor was not there, and hence the name inhibitor. Okay. Let us look at one more example. Which one shall we look at? We looked at this, well, there are several. What I wanted was, where it happened to that? Okay, I think I'll just write it down over here. Okay. The question, the next example, although it is not there in that form, is the following: for which of the kinetics below plug flow reactor will be better than CSTR. Okay, we have a catalytic reaction whose rates are given, and there are 3 or 4 different types of rates. So, question is, for which of these kinetics the plug flow reactor is better than CSTR, and what are those rates? The rates we have is as follows: R equal to K into partial pressure of A square, or R equal to K into partial pressure of A divided by some K prime plus partial pressure of A, yet another K into partial pressure of A the whole square divided by K double prime per partial pressure of A the whole square, and yet another K into partial pressure of A plus K double prime plus partial pressure of A plus K triple prime partial pressure of A the whole square. Okay. Now, this is all qualitative. Okay. There are no numbers expected here. So, how do we decide on this? So, first thing that we have to recall is for what kinetics PFR is better than CSTR. Even before with that, let us recall the characteristic of PFR and characteristic of CSTR. So, what happens in a PFR? Okay. In a PFR, I am going to show now what will be my partial pressure, okay, along the length of the reactor. Partial pressure will gradually decrease from the inlet condition. And what happens in a CSTR? In a CSTR, what happens? My partial pressure from the inlet decreases instantaneously to the lower value. Let us say that lower value is same in both CSTR and plug flow reactor. So, in a CSTR, there is a sudden decrease in the concentration and reactions occur at this lower concentration. In a plug flow reactor, the decrease is gradual and therefore, the reactions occur at concentrations which are gradually decreasing. So, when we want to answer this question whether plug flow reactor is better than CSTR, the answer lies in realizing that if the rate of reaction is increasing with increase in partial pressure, then what will happen? The rate will decrease also gradually. But if for example, there are situations where the rate of reaction actually increases up to a certain point and then starts decreasing. So, at high concentrations the rate is low actually and reaction rate is high at some intermediate concentration. If such reactions exist, then we have CSTR which is better than plug flow reactor, because what will happen is at high concentration the reaction rate is low. So, when the concentration reduces suddenly in CSTR, the reaction rate will actually increase suddenly, whereas in plug flow reactor the reaction rate will gradually increase. So, we need to examine these rate expressions in the light of this observation and see which one of them have rate increasing with increase in partial pressure. So, let us look at the first expression, just a sketch, this will be Pa square. What about the second expression? Second expression, it will increase and reach a saturation. What about the third one? Third one also it will increase and reach saturation and S curve. In fact, this will be hyperbola, this will be S curve. But what about the fourth reaction? The fourth one, you see numerator is going first order in partial pressure, the denominator is going in the second order. So, initially rate will increase, but as partial pressures increases, what will happen to the rate? At very high partial pressure, rate will be inversely proportional to the partial pressure. So, rate will go down. I think the answer is clear now, that for this it is a for this it is a PFR, this is also PFR, this is also PFR, but only the third the last one it is CSTR. So, we have answer to our question. So, these are the few examples which we saw, which illustrate the ideas that we have seen in more detail by looking at few of the examples. So, we will stop here for this session and continue with our or initiate our discussion on heterogeneous catalysis in our next session. Thank you.